Now, let's talk about Gaussian distribution, which is really popular in machine learning and in engineering in general. Okay. Gaussian distribution, also known as normal distribution, is given by this equation. And as you can see, there is a mean and the variance, and we have exponential function, and it looks like this. It's like a bell shape. Okay. So it's really smooth curve, and it is a symmetry. It means left side and right side, they look similar. And there are two conditions as a probability distribution. First one is it should be positive everywhere. So it looks like it is a zero around here, but technically it's not zero. It's really small number, but still it is positive. Probably we need equality here too. But everywhere it is positive. It cannot be zero. Okay. And summation is 1. Okay, then why is Gaussian distribution so popular in machine learning and in engineering? There are a couple of reasons, and I think the Gaussian is simple. Okay. And it is useful in many ways. So let's take these reasons step by step. So first, Gaussian distribution can be defined by simple sufficient statistics. So in the previous slide, I said Gaussian is defined by a mean and variance. Okay, and then this mean and variance can be estimated by some statistics. Okay, so sample average can estimate the parameter mean. And also variance can estimate parameter variance. So these estimates are quite simple. We can calculate sample average and sample variance simply. So we can actually estimate the parameters of Gaussian distribution, and that is it. So we can define Gaussian distribution based on samples simply. That's the first reason, I guess. And the second one is that Gaussian is simple to calculate posterior distribution. So to understand these things, we need to understand the concept of conjugate distributions. Okay, if p of theta given x, this one is posterior, is in the same family, such as Gaussian, as p of theta. For example, this posterior is Gaussian and p of theta is Gaussian, then they are conjugate distributions. So as long as they are in the same family, then they are conjugate distributions. And p of theta is conjugate prior for p of theta given x. So to remind you of base rule, let me put the equation here. P of theta given x is p of x given theta and p of theta given over p of x. And p of x is usually, we use likelihood and the prior and the theta. So this integral is almost impossible in many problems. So that's why this p of x is a headache in machine learning many times. Okay, so we are talking about this prior and posterior. And so the likelihood and the prior are Gaussian, then the posterior distribution is Gaussian. Okay, that's already proved. So now, if we know this prior distribution and the likely distribution, then we can actually simply calculate these posterior distributions. We don't need to calculate this p of x in this case. Look at this one. P of x is actually is marginalizing this part to make posterior to be a distribution. Okay, so if this one is a Gaussian, we already know that, and then what we need is mean and variance. Okay, so So simply we can actually calculate posterior distributions without this term. Okay. And also the product of two Gaussians is again Gaussian, like this. Okay. And also the sum of two independent Gaussian random variables is Gaussian. So it's really convenient to estimate some distribution. Okay, and finally, Gaussian distribution is useful in many cases. For example, noise and errors can be modeled by Gaussian distribution. Okay, most of the time we assume that the errors or noise are Gaussian. And the central limit theorem talks about another good feature of Gaussian distribution. When independent random variables are added, their sum or average tends toward a Gaussian distribution. Even if the original variables are not normally distributed. Okay, here is an example. So we are playing a dice, okay, and if n is 1, which means we are not adding two numbers, then what is the probability of all the events? For 1, the probability is 1 over 6, and for 2, the probability is 1 over 6, etc., etc. So when n is 1, if we are not adding the random variables, then it is 1 over 6. It's uniform distribution. Okay, now we want to add two numbers. Okay, so we play the dice twice, and then we add two numbers. Okay, then when we play one dice, then we could get 1, 2, 3, 4, 5, 6. And when we play one more time, we can have 1, 6, okay, and etc., etc. Then if we add 1 and 1, then we will get 2, and we get 3, and 4, 5, 6, 7. And what about this one? The first dice has 2, and in the second dice we have 1, then we have 3, and then 4, 5, 6, 7, 8. Okay, then look at this one. We, in this case, we have 1, 2, and we have 2 3s and 2 4, and in this case we have another 4 here, 3 and 1. So we have 1, 2, and 2, 3, and 4 4s, and 5 4s, etc. So we have 2 and 7 and 12 here. We get a lot of 7s. Okay, how can to get 7, it could be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So we have 6 7s because we have 36 cases here, and 6 cases means the probability of 7 is 1 over 6. Okay, and we have only 1 2 here, so 1 over 36 is here, and we can get 12 by 6 and 6. So we have only one case, so 1 over 36. We have the same probability as event 2. Okay, so next, if n is 3, so we are adding 3 numbers. Then it goes from 3 to 18. And again, we have lots of 10 and 11, but we have 1, 3, and 1, 18. And if we keep adding the numbers, then from this uniform distribution, and this is a triangle, and this is a little smooth, and it goes smoother, and when n is 5, it looks like a Gaussian. Not exactly yet though, but still it looks Gaussian, and if we keep increasing n, then eventually it becomes Gaussian. So even if the original variables are not normally distributed, if we add or if we take average of these events, then it converges to Gaussian. So Gaussian is beautiful in many ways. And Cramer's theorem it says something about Gaussian distribution too. Okay, so let me just note that x1 plus x2 is Gaussian, then x1 and x2 are Gaussian too, and vice versa. Okay, so I think this is a little beyond what is necessary, but if you're interested in machine learning and if you want to go deeper, then you can study this by yourself. And this slide is about Gaussian mean and variance. Actually, a sample mean and sample variance are sufficient statistics of Gaussian. So as long as we can calculate the average and as long as we can calculate the variance, then we can estimate the mean and variance. Okay, then these are enough to define Gaussian distribution. Okay, so in this equation, as long as we have a mean and variance, then we can define this function. In the beginning of this chapter, we talked about the probability and statistics. Okay, this one is actual theoretical value, and variance is also a theoretical value. So if we have a mean and variance, then we can define Gaussian distribution. But most of the time, mean and variance are unknown. So we have to estimate this mean and variance based on the data samples. So mean can be estimated by average of the samples, and the variance can be estimated by some function. So these functions are actually sufficient statistics of Gaussian. And in the previous slide, we talked about Gaussian distributions for a scalar in the one-dimensional space. And now, if X is in a vector space as a vector, and Gaussian distribution can be defined by this. And instead of just the variance, scalar variance, then we have a matrix here. And the mean is a vector too. Okay. And it looks like this. This is a Gaussian distribution contour. So this one has, think about this Gaussian distribution in one-dimensional space. It looks like this. So around the mean, we have high probability, and as long as it goes away from the mean, then the probability goes down. So likewise, in the two-dimensional space, this one has the highest probability, and we have a lower probability on like this. And in these equations, actually this part is a square of Malone-Beast distance. Malone-Beast distance can be defined by this one. If this one is identity matrix, then it is a Euclidean distance. So Malone-Beast distance is a generalized version of Euclidean distance. Or Euclidean distance is a special case of Malone-Beast distance. Okay, and you can prove that if two Gaussian variables are uncorrelated, then they are independent. Usually, in general, even though two variables are uncorrelated, they might be dependent. But if these two variables are Gaussian and they are uncorrelated, then they are independent. Okay, you can prove this by yourself. And let's talk about transformation of a Gaussian variable. So when y is ax, a linear transformation, and p of x is given by this Gaussian expression. X is a Gaussian random variable. And then x is a vector. So then we have this Gaussian distribution. And then y is a Gaussian with mean and variance as follows. And then let's calculate the mean of y. So expectation of y is actually expectation of ax, and a is constant, so it is actually a times expectation of x, which is a mu. And the variance of y is defined by this one. And in this equation, we can replace y with ax. And expectation of y is, we already know that, so which is a times mu. So if we derive this equation, then finally we have this term. Okay, then the py is, we already calculated this mean and variance. So p of y is defined by this one. So this is a mean and this one is a covariance matrix. Okay, this one is actually the same as this one. So this one is about the p of y and this one is about p of x, right? So this one says 1 over determinant of a times p of x. P of x is actually this Gaussian distribution. Since y is ax, then x is a inverse y. So we have a inverse y here because we want to use n x given mu and sigma. Okay. And the next one is whitening transformations. It transforms a random variable vector x with a covariance sigma into a new variable vector whose covariance is the identity matrix. So let's say whitening matrix is something like this. Then the covariance of y, y is a sub w times x. Then covariance of y is identity. Then a sub w is a whitening transformation. And with the eigendecomposition of this covariance matrix, then a sub w could be this one. Okay, eigenvalue matrix to the power of 1 over 2 times eigenvector matrix transpose. And let's take a look at this figure on the right side. So let's say this one is original Gaussian distribution, and we want to transform this one into some other vector space by matrix A. Then in general, y has this distribution. Okay, and in this case, this one is mean of this vector, this distribution, and we have lots of ellipses like this. But if we transform this one with the whitening transformation, then definitely the covariance matrix should be identity matrix. And this one is the mean of this distribution. And we have lots of circles, not ellipses. Okay. And we want to compare a couple of different transformations here. So let's say this one is our distributions. Okay, so to be exact, it looks like this. Okay, then if we standardize this distribution, then we have this direction, but on this dimension, the variance is 1. In this dimension, variance is 1. Okay, but still there is correlation like this. And if we decorrelate this distribution, then we can rotate this one. Okay, so we rotate this one in this way. So this one and this one, they are orthogonal and they are not correlated at all. But we didn't change the variance. This variance might be 2 and this variance might be 0.7 or something. But if we apply whitening transformation to this distribution, then we have the variance 1 in this dimension, and in this dimension we have variance 1, and there's no major axis here, which means there's no correlation between this and this. Okay, so it's whitened. In general, we'll talk about transformed densities. So we already talked about transformed densities when it is Gaussian distributions. But in general, given these transformations with the p of x, then what is p of y? Okay, so that's the question. Then to understand the meaning of this question, then let's check this simple example. If y is 10 times x, it's a really simple transformation. Okay, and then p of x is uniform in this range, then what is p sub y of 5? What is it? So this is transformation. So if y is 5, then x is 0.5. Then what is the probability of p of 0.5 in x space? 0.5 has 1 here. P of 0.5 is 1. Okay, because the sum of this probability should be 1. Okay, then everywhere we have 1 as probability. Okay, then how about y? Since this one is just the transformation is just about scale, then we can see that y goes from 0 to 10 because x goes from 0 to 1 and the transformation is multiplication of 10, so y goes from 0 to 10, and then what the probability should be uniform distribution. Okay, because we just changed the scale. Then what is the probability of this uniform distribution? It should be 0.1, right? So that the area of this can be 1. So since we have 10 here, then it should be 0.1. Okay, then what can we see from this simple example? If we have 10 here, then p of y 5 is 0.1. You see that? From x to y, we multiply 10. Then from p of x to p of y, we divide this by 10. So p of 0.5 divided by 10, which is 0.1. You see that? We transformed so that in the y space it changed. But as long as we know that this transformation and the p of x, then we can calculate the p of y. So this calculation is based on this. P sub y of y is actually p sub x of x times this volume change. Okay, how much change? So this one says when x is change, the ratio of the change of x to change of y. Okay, and in a linear transformation like this, we already talked about this one. Determinant A means the volume change from x to y. So P of y is P of x divided by volume change. So this 10 is actually volume change. So we divided this 10 here. Likewise, we divide this volume change. Okay, so we have been talking about the Gaussian distributions for a while. Then Gaussian distribution is really beautiful and everybody loves Gaussian, but still there is some limit in Gaussian distributions. First, there are too many parameters. Think about the mean and the variance. If the dimension is d, then for mean we have d parameters. Right? So mean is a vector in d-dimensional space, so we have d parameters, and the variance is actually d times d matrix, but this variance is actually symmetric. So think about this covariance matrix. This is diagonal elements, and these off-diagonal elements are the same as here. So if we count the number of parameters here and D, then it is actually this one. Okay, because in the covariance matrix we have this one, this many parameters, and in the mean vector we have D parameters. Okay, and then we have too many parameters, and if that's the problem, then we can simplify the problem, or we can approximate. So we can reduce the number of parameters with some assumptions or approximations. So in general, we have this many parameters for covariance matrix, but sometimes we can have diagonal matrix. So in this covariance matrix, we set 0 here, and we have some numbers. Okay, on this diagonal line. Then we have D parameters for covariance matrix, and we have D parameters for mean vector. So in total, we have 2 D parameters. But if it is still too many parameters, then we can reduce one more time. So instead of having different variance on this diagonal element, then we can have the same value, like this. So in this matrix, it is actually identity matrix, but we have a different scale, sigma. Okay, so we have only one parameter for a covariance matrix if it is isotropic covariance matrix. Okay, so we need the D parameters for mean, and we need one parameter. So in total, we need D plus one parameter. So in general, we have too many parameters, but if that's the problem, then we can reduce the number of parameters based on some assumptions or approximations. Okay, and there is another problem, another limit in Gaussian distributions. It is intrinsically unimodal. Unimodal means we have one bump here in Gaussian distribution. Okay, so it cannot provide a good approximation to multimodal distributions. What if the distribution looks like this? Okay, then the one single Gaussian cannot model this kind of multimodal distributions. Okay, we have this kind of cases many times. Think about the score in physics. When we take an exam in physics, then it is a 0, then it is 100. Then usually we have this kind of distribution. You know, in physics, if you know something, then everything is clear. It's simple. If you don't understand, then everything is really complicated. So there are lots of students around here and lots of students around here. Okay, so it's a unimodal distribution. Sorry, it's multimodal distribution. We have 2 modes here. So Gaussian cannot actually model this kind of samples. Okay, there's a limit. Then we can overcome this limit by combining many Gaussians. So for example, we are going to talk about mixture of Gaussians later. Basically, if we have these kind of samples, then we will use 2 Gaussian distributions, one for this and the other one for this. Okay, so we have a mixture of 2 Gaussian distributions. Okay, before finishing these chapters, then I might have to say that this stationarity or stationary property is really important in pattern recognition or machine learning. So what is a stationarity here? The process is stationary if the distribution does not change over time. Like if the distribution doesn't change, then the mean and variance, these statistics should not change, right? So parameters like mean and variance don't change. Actually, the stationarity is more than just the mean and variance. It should have the same kind of mean and variance and kurtosis and skewness, etc., etc. But usually we just check mean and variance. Okay. And stationarity is an underlying assumption. This is really important. Underlying assumption of many statistical algorithms for time series data. Okay. Which means, okay, let's assume that we have these kind of signals. Then we have this part for training and we have this part for testing. And it means when we train with these samples, we assume that the next samples have the same kind of distribution, so that the model which is trained based on these samples can work with these samples. Okay. But sometimes, many times maybe, this assumption of stationarity is too restrictive. Many times we have a non-stationary processing like this. Okay, so if this is our data samples, then we can use this part for training, for this part for testing. So if we use this part for training, then maybe model might recognize the mean around here. But for testing, the mean is around here. It's completely different, right? So probably the model which was trained with these samples cannot work with these samples because these samples are completely different from these samples. But if it is a stationary, like this, then if we train our model with these samples, then it will work with these samples quite well. Okay. So most of the time, the models assume that the process, the signals are stationary. But if your data is non-stationary, then you have to handle these situations. Okay. Okay, so before finishing this chapter, let me just introduce a couple of basic distributions. First one is uniform distribution. I think you're already familiar with uniform distributions. Uniform distribution has the same kind of probability no matter where it is, as long as it is between A and B. Okay, so the same kind of probability. And the expectation is given by this variance and entropy. In next chapter, we're going to talk about information theory, which includes entropy. So don't worry this quantity. Okay. And the next distribution is Bernoulli distribution. It's about discrete probability distribution. Okay, like a coin tossing. So when we toss a coin, then we have either of head or tail, right? So the probability that the result is head is P. And then the probability that the result is tail is 1 minus P, right? And the probability of X could be head or X could be tail, okay, is defined by this one. So if X is 1, which means head, then P of 1 times 1 minus P times 0, so it is P. If X is tail, which is 0, then P of 0 times 1 minus P times 1 minus 0 is actually 1 minus P. So if it is a tail, then we get this one. If it is head, then we get this one. And expectation is P and variance is like this. And binomial distribution is actually the probability of observing m occurrences of X is 1. So it's basically based on the Bernoulli distribution, but it tosses like n times And then we are interested in the probability that how many times we get hat. So what is the probability that we get m times hat? Okay. So in this distribution, we have n and we have p. P is a probability of hat. Okay, and we tossed n times, then what is probability that we get m times hat? Okay, then in that case, out of n we need m times hat, then we have to multiply this from the Bernoulli distribution. And expectation is quite trivial, n times p, and the variance is trivial. Okay. And the next one is categorical distribution. This categorical distribution is really popular when we are working on something like image classification. So we have 10 classes, okay, for example. Then the k is 10 here. So we apply this Bernoulli distribution to 10-dimensional binary variable x. And each of this x element could be either 0 or 1. So we have 10 classes. Okay, then either each of these elements could be 0 or 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry. So we have 10 elements. Then there is another constraint here. The sum should be 1. So it means only one element could be 1 and the other element should be 0. So 0, 0, 0, 0, 0, 1, 0, 0. Which means the label, the class of this given image is this one. Okay. And the sum of the probability is 1, which means it could be 0.1, 0.1, 0.1, and 0.2, then 0.05, 0.05. Okay. So this one is a generalization of Bernoulli distribution. In the Bernoulli distribution, we have a p, right? So head is 0.7 and tail for tail we have 0.3. And when we toss, actually, if we have head, then it is 1. If it is a tail, then it is 0. Likewise, we have 0, 0, 0, 1, 0, 0. It corresponds to this thing, and these values correspond to these numbers. Okay. And the multinomial distribution is actually can be interpreted as extension of categorical distribution. So in the previous slide, we talked about Bernoulli distribution to binomial distribution. Likewise, in this case, from categorical distribution to multinomial distribution. So they have the same kind of relationship. Okay, and the next one is Laplacian distributions. Laplacian distribution is probably we're going to talk about this Laplacian distribution a couple of times, and compared to Gaussian distribution. Gaussian distribution looks like this. And compared to the Gaussian distribution, Laplacian distribution is more sharp or picky around this mean variable, mean vector. Okay, and then the last one is beta distribution and Dirichlet distributions. These are prior distribution for probabilities with shape parameters. So I'm not going to cover this slide. So if you're interested in, then you can study this by yourself. Okay, that's it. So if you have any question, then email me.